Alright, so I was asked to make a video about transformations, and quite honestly it didn't even occur to me until I was just about to hit the record button and I was writing this, that whoever asked me to do this by writing it on my board might have meant algebraic transformations, because we've covered both. We've done some geometric transformations and we've done some algebraic transformations. So let me go ahead and start with geometric transformations because that's what I was thinking. And then from there, I'll also talk to you briefly about algebraic transformations so we can get a little bit of both. First off, geometric transformations are rotations. Let's give you an example. Rotations or reflections. If it's reflected, it basically flip-flops. Or translations, which just means I'm sliding it. Up, down, left, right, that's a translation. Or dilations, which I cannot do with this scissor because I don't have these scissors because I don't have magic powers. Dilations are enlargements and reductions in size. So first, let's go with the easiest one, reflections. You have to have a line that you're reflecting across. You have to know what line am I reflecting across. And depending on what line, there are some basic rules we can try to remember. Is anytime you reflect across the x-axis, it just changes the sign of your y. Whatever the sign of y was to begin with, it just changes. It doesn't switch or anything. It stays in the same place. It just changes the sign. If you reflect across the y-axis, it's the opposite thing. You change the sign of x. And if you reflect across the line y equals x, the line y equals x, and this is an important line to remember, is like a perfect diagonal with a slope of 1 that goes right through the origin. That's the line y equals x. If you reflect across that, like let's suppose I had the point 1, 4, you flip-flop the coordinates. It would become 4, 1. Okay, there's another thing that can happen. You can reflect across a specific line that you're told, like a horizontal line or a vertical line that is not the x-axis or the y-axis. So for instance, in the assignment that you did recently, or that my students did today, it asked you to take this triangle that has coordinates I, L, and J, or excuse me, vertices I, L, and J, and reflect it across the line x equals -1. Well, before you can do that, you have to know where that line is. You have to know that x equals lines are vertical lines. In other words, I'm going to go on the x-axis to -1, and I'm going to go up and down from that, all the places where the x value would be -1. So that's this line right here. Okay, so basically there's two ways to look at it. You can do it visually. And the thing you have to know is that with a reflection, the reflection image, remember pre-image is the beginning, image is the ending. The image is always going to be just as far away from the line of reflection as the pre-image was, but on the opposite side. For instance, let's look at point L. It is 1, 2, 3 boxes to the right of the line. So now it's going to be 1, 2, 3 boxes to the left. That's where the image of L will be. Same thing with J. 1, 2, 3, 4 to the right, so I stay on that same line and go 1, 2, 3, 4 to the left. And finally, I is 1 to the left to begin with, so it's going to go 1 to the right. So my image of that triangle will look a little something like this. Okay, so I just did that visually. You can also do it with the coordinates. I could take the original coordinates of I, L, and J, so that would be for I, that was -1, -2. L was originally at 3, 1, and J was originally at 4, -3. Excuse me, I wrote 4 there. J is at 4, -3. Okay, and knowing that I'm going to reflect it across x equals -1, what's going to change is the x value. The y value is not going to change. Just the x value is going to change. So it's going to go across that line, And if I look at this and I see, I'm sorry, I think I did this one wrong. I think I might have done them all wrong. I sure did. No, I didn't. Yep, I did. All right, let's try that again. Sorry. When I was looking at how the coordinates, I actually looked at the dotted line instead of the y-axis. So I is actually at -2, -2. L was originally at 2, 1. And J was at 3, -3. Okay. Now, since it's across the x-axis, we just said it, the x is what's going to change, the y is not going to change. And so I basically need to see how far this x value is away from -1, and then go in the same distance in the other direction. In other words, -2, think on a number line. -2 is 1 unit below -1, smaller than, or to the left of. So I'm going to go 1 unit higher than -1, which is 0. The y value didn't change. +2 is 3 units bigger than -1. Okay, to get from -1 to +2, I would add 3. So I'm going to go the opposite way. From -1, I'm going to subtract 3. That would be -4, 1. And finally, 3 is 4 units bigger than -1, so I want to go 4 units smaller than -1, so that's -5, -3. And you should find that those are exactly where I drew the points just a second ago. Okay. Next, rotations. Here are the basic rules for rotations. One thing that you do need to know about rotations, if they don't specify, if they don't tell you clockwise versus counterclockwise, you have to assume counterclockwise. If they don't tell you whether it's clockwise or counterclockwise, you assume counterclockwise. Okay, so counterclockwise, remember, is like this, going against the clock. It's basically the same direction that we name our quadrants in when we're talking about the coordinate plane. Like you have the first quadrant, then you go around this way. Second quadrant, third quadrant, fourth quadrant. All right, so here are the rules. If you rotate 90 degrees counterclockwise, the two coordinates switch places, and whatever the sign of y was originally, it's going to change when it goes into the x spot. So if this was negative, this would now be positive. Whichever way it was to begin with, it's going to change. 180, both of the signs are going to change, and they're not going to trade locations. They're going to stay in the same order. 270, they're trading locations again. The order is swapping. And this time, you look at whatever the number was, the original x, it's going to be in the y spot now. You also need to change its sign. Now, the nice thing about if you know counterclockwise, then you kind of know clockwise, because if I go, let's say I start here. If I go 270, this is 90, 180, 270. Okay, if I do 270 counterclockwise, that's the same as 90 clockwise. So if you're asked about 90 clockwise and you know what 270 is counterclockwise, well, you're going to get the same answer. And it works the same way up here. If I go 90 counterclockwise, that would be right here. That's the same thing as going around 270 clockwise. So 90 counterclockwise is the same as 270 clockwise. Did I say that right? 90 counterclockwise, these are all counterclockwise, is the same as 270 clockwise. 180, it doesn't matter which way you go. 180 is 180. If I go halfway around or halfway around, I'm still halfway around no matter which way I went. So looking at this problem that my students did today as well, I have this triangle, and it has coordinates it has, I keep saying that, vertices M, T, and Y. I'm going to make this bigger so you can see it a little better. Maybe I can see it a little better too and not make a mistake this time. How's that? So M is at -1, 1. T is at -5, -2. And Y is at -1, -4. And there's my triangle. And the goal here is to rotate that 180 degrees. Well, if I know these rules, I know that 180 degrees, the order of the coordinates is going to stay the same. The order of my coordinates stays exactly the same, and I'm just going to change signs. So that means my new M, or M prime, will be +1, -1. My new T, T prime, will be +5, +2. And my new Y, Y prime, will be +1, +4. So let me graph that. 1, -1 for M prime. 5, 2 for T prime. And 1, 4 for Y prime. And of course, keeping in mind that I'm freehanding this, basically you should still be able to see that that's like I rotated this one over here. I turned it 180 degrees, and now it's up here. It looks the same thing. It looks like the same thing. Okay, next we have well, we're not going to really talk about translations, actually. Translations are pretty self-explanatory because it tells you, when it tells you a translation, it tells you you're going to do x + 3 and y - 2. So you just do whatever it tells you. Dilations are the other one that can get a little bit tricky. Okay, if the dilation has center 0, 0, then basically you're going to multiply everything by the scale factor. So for instance, if I had, let's say I had a triangle right here. Okay, and I said I'm going to dilate this triangle by a scale factor of 2. That means I find this coordinate, these coordinates, and I make it twice as big. So it would be right here. And this coordinate, twice as big. So it would be up here somewhere. And this coordinate, twice as big, so it's over here. And so, I'm sorry, that's kind of out of line. My new one is like this. So for instance, if this was 2, 3, this would be 4, 6. Everything times 2, if my scale factor was 2. This example up here is if my scale factor is 2/3. Notice that not only did the coordinates get changed by 2 for a scale factor of 2, but the side length would be twice as long, twice as long, twice as long. Now the other thing is, if it's a dilation with a center not at the origin, not at 0, 0, it helps to know this. The new point and the old point will always line up perfectly with the center of dilation. If you look at these two pictures, which is in the Analytic Geometry book on page 252. This picture right here, and I will move it a little closer for you, the one on the left, it shows you a triangle and another triangle. Okay, the black one I think is supposed to be the original, that's the pre-image, and the red one is the image. Look at the dotted lines connecting the points. If you connect a point to its pre-image, in other words, the dotted line connects B prime back to B, or it connects A prime back to A, or it connects C prime and C, eventually they all meet, and the place where they all meet is the center of dilation. Same thing's happening over here. If you take a point, and the point that it used to be, R prime came from R, so you connect them with that line. Q prime came from Q, so we connect those two with a dotted line. And P prime came from P, so we connect those two with a dotted line. Those dotted lines will all come together at a single place, and that single place is the center of dilation. Now both of these examples have a center of dilation at 0, 0, at the origin. But it's possible for your center of dilation to be somewhere else. And that's something you could be asked about on your EOCT. Like, for instance, if you had a graph and it showed you this rectangle, and this is all freehand, so it's not going to be perfect, and it showed you this rectangle, and that's definitely not going to be perfect. That's too wide. Let's pretend I didn't do any of that. And it asked you to find the center of dilation. Here's what you would do. You would connect a point, and the other point it should go through. And all of these dotted lines should come together in one place. That's the center of dilation. Now, you have listened to a lot of stuff on geometric transformations if all you wanted to know was algebraic transformations. So here you go. Ready for you. Algebraic transformations, the time we have used them the most in analytic geometry is with quadratics. And usually with quadratics in vertex form. Okay, so this is a quadratic equation in vertex form. Basically, here's how it works. A minus or a plus, which we don't actually see a plus, so a plus or a minus, an invisible plus sign or a minus, that tells us whether or not there's a reflection. If there's a negative, let me bring this over here, that means the whole thing has been reflected across the x-axis. So now my parabola is opening down and not up. That's what that means. When we're talking about it's been reflected, we're talking about from the parent function. The parent function is your basic garden variety y equals x squared. Okay, so we're comparing this back to y equals x squared. There's a negative here that's not there in y equals x squared, so that has been reflected across the y-axis. The next thing that's here that's not there in y equals x squared is a number out front. If there's a number other than 1 out front, that's what we call a vertical stretch. This has a vertical stretch by a factor of 2. That basically means every single point would now be twice as high above where it used to be off the x-axis. Now it would be here and here. This would get narrower because all the points would have twice as much height, basically, off the x-axis as they used to. Next we have pluses and minuses. Pluses and minuses are always translations or shifts. Sometimes we call it a translation, sometimes we call it a shift. Okay, if it happens with the x, since x is left and right, then that's left and right. So that's what we call a horizontal shift. If it happens out in the back, remember we did talk about how this is the k and we could move it over here. Remember, HK is the vertex of a parabola, so the K is the Y. So this number really goes with the Y. Okay? Up and down is vertical, so this is a vertical shift. Now, anything that's happening outside of parentheses, what you see is what you get. So this vertical shift is just up 3, which is kind of what you would expect 3 to do vertically. In other words, positive numbers would take you up, negative numbers would take you down. Inside the parentheses with x, though, just like if I was pulling this out, I would have to change the sign. Everything's backwards. This doesn't go left 4, even though it's negative. A negative takes me to the right. A positive would take me to the left. So this is actually sending me right 4 units. So it's like my parabola. Let's say we had the original parent function. It's like it got skinnier, that's the stretch, moved to the right 4, and then up 3. So now it's up here. And it flipped over. So this is the result. And that is what algebraic transformations are all about. The end.